Welcome to The Explainer. Today, we're diving into a really bold new vision for the future of AI. And it's a future that's not just about making AI smarter, but about making it sustainable. Because as we're about to see, those two things are becoming one and the same. So let's just kick things off with a fact that is, well, it's pretty staggering. If you train just one of today's top-of-the-line AI models, you can use the same amount of electricity as hundreds of American homes consume in an entire year. That is a massive energy footprint, and honestly, it's only getting bigger. And this quote, it really nails the core issue here. You see, AI and the hardware it runs on are kind of locked in this dance. Smarter AI needs more powerful chips, and those better chips let us build even smarter AI. It's a great cycle, but it's also creating a sustainability crisis that could, ironically, stop all that progress right in its tracks. So this is the hidden cost of all this AI brilliance we're seeing. It has this insatiable appetite for energy. And we've hit a point where the way we're doing things is becoming just fundamentally unsustainable. Here's where the real problem lies. The AI algorithms, the software brain, they're evolving at a wild pace. We're seeing huge breakthroughs in a matter of months. But the hardware body, the actual silicon chips, that takes years to design and build. And this growing gap between the speed of software and the speed of hardware is where things start to go wrong. And that disconnect, it's creating this massive bottleneck. There's a problem known as the memory wall, and it basically means we are wasting incredible amounts of energy, which in turn threatens to stall the entire AI revolution. So what exactly is this memory wall? Well, imagine a brilliant chef in a giant kitchen. This chef can cook faster than anyone, but they spend most of their time and energy just running back and forth to a pantry that's all the way on the other side of the room. That's pretty much what's happening inside our computers. We're now literally spending more energy just moving data around than we are on the actual thinking. Okay, so what's the fix? How do we get out of this mess? Well, the solution is this really radical idea called AI and hardware co-design. It's about tearing down the walls that have separated the software people from the hardware people and designing everything together in sync right from the very beginning. And this is a great visual for that new vision. It's a layered approach. You see, down at the bottom, you've got the physical hardware. In the middle, the AI algorithms. And up at the top, the real-world applications. And the magic here is in the cross-layer synergies, making all three layers work together perfectly by design. Let's start at the bottom, the foundation. That's the hardware itself. New ideas here, things like 3D chips or even hybrid quantum classical systems, they completely change the physical rules of the game. They set a whole new limit for what's even possible. Then in that middle layer, you've got the algorithms, the actual AI models. And the goal here is to make them hardware aware. Think of it like a Formula One driver who knows every single quirk of their car's engine. The AI is designed to perfectly exploit the strengths of the specific chip it's running on, just squeezing out every last bit of performance. And then, right at the top, you have the applications. This is really the why behind everything we're doing. Discovering new medicines, building better energy grids, solving real human problems. This layer is so important because it tells the hardware and algorithms below what they actually need to do. It defines what success really looks like. You see, this whole co-design thing, it forces us to completely rethink how we even measure success. For years, the industry just chased raw computing speed, something called flops. But this new vision suggests a totally different metric, intelligence per joule. The new gold standard isn't about being the fastest, it's about being the most efficient. How much actual, useful insight can we get for every unit of energy we burn? All right, so let's get practical. How does this co-design approach actually work? Let's start from the ground up with the silicon itself. What does the hardware of tomorrow really look like? To break through that memory wall, researchers are looking at some mind-blowing ideas. Like, we can stack chips in 3D, almost like skyscrapers, which dramatically shortens the distance data has to travel. We can even do the computations inside the memory itself, which gets rid of that trip to the pantry altogether. We can even use light, photonics, to move data instead of electricity, making it way faster and way more efficient. But look, this is crucial. It's not just a hardware problem. Better chips are only half the story. The AI models themselves have got to evolve. The future isn't about just building bigger and bigger models. It's about making them fundamentally smarter. For the longest time, the thinking in AI was pretty simple, right? If you wanted a more capable model, you just made it bigger. More data, more parameters, more compute power. But is that really the only way?
Okay, now this chart shows something really fascinating and honestly a little counterintuitive. For a long time, better accuracy did mean a bigger model. But look at that trend line. Over time, the model size you need to hit high accuracy is actually going down. Thanks to smarter algorithms and co-design, we are learning how to get more intelligence with less horsepower. This is the very definition of working smarter, not bigger. Which brings us to the moonshot goal of this entire roadmap. The target over the next 10 years is to get a staggering 1,000-fold improvement in the energy efficiency of AI, both for training new models and for running the ones we already have.
Now, 1,000x improvement. That sounds almost impossible, right? But here's how the roadmap gets us there. It's not one single magic bullet. It's about compounding gains across the whole system. A 10x improvement from smarter algorithms, a 20x improvement from new silicon, and then another 5x improvement from better system-level design. Each one multiplies the others, and that's what makes this moonshot actually reachable. So this is where we get to the big so what. Why does any of this matter to you and me? Well, this isn't just some abstract problem for engineers. It's a race that has huge implications for our energy grids, our economy, and really the future of technology itself.
I mean, think about this. AI data centers are already using as much power as entire countries. And this chart really lays out the problem. In the US, for instance, power generation has been basically flat for years. But the demand from AI is about to explode. We are on a collision course where our own energy infrastructure could become the main thing holding back AI.
And it's not just a power problem, it's a practical one too. Right now, a shocking 95% of corporate AI pilot projects never actually get fully deployed. They get stuck in the prototype phase, a lot of the time because the cost and the complexity of running them at scale is just way too high. And that is why this vision is so incredibly important. This is about way more than just faster chips. It's about creating a future where powerful AI isn't just a tool for a handful of giant companies, but is accessible, affordable, and sustainable enough to unlock the next wave of scientific and societal breakthroughs for all of us. So, as we look ahead, we're really at a fork in the road. Do we keep going down this path of brute force, building bigger and bigger systems that eat up more and more energy? Or do we pivot to a new era of sustainable intelligence? The choice we make in the next few years is going to define the future of AI for generations to come.